Array antennas, problems on linear arrays, part 1, series on antennas and wave propagation, lecture number 3.15. Array antennas are most versatile antenna systems widely employed in the design of modern wireless communication systems, especially in radar systems. In the present session, we focus on problems and their solutions, problems being set on arrays, especially on linear arrays. These problems cover directions of maximum radiation, directions of nulls, directions of minor lobes, directivity, half power beamwidth, and also some other important parameters pertaining to linear arrays when they are operated in broadside mode, end-fire mode, and also in end-fire mode with increased directivity. We begin the session by considering a problem, example 1. Find total number of lobes, number of minor lobes, width of the main lobe, and the width of minor lobes, all in psi domain in the radiation pattern of a 20-element isotropic linear array. We are asked to determine several aspects of the radiation pattern of a 20-element isotropic linear array in psi domain. Psi is array phase function. It is given by beta d cos phi plus alpha. Alpha denotes phase progression pertaining to excitation currents. Phi is observation angle. D is element spacing. Beta is 2 pi by lambda. Lambda is wavelength corresponding to operation frequency of the array. With this small explanation regarding psi array phase function, now let us move to the solution. All the required information in the problem is related to the number of elements of the array. Total number of lobes in psi domain is given by n minus 1. N here is number of elements of the array given as 20. So total number of lobes is 19. Number of minor lobes is n minus 2. It becomes 18. Width of main lobe in psi domain is 4 pi by n. It turns out to be 0.2 pi radians. Width of main lobe, it is 2 pi over n. In the present case, it turns out to be 0.1 pi radians. We move to another problem, example 2. Find the visible range of a 12-element isotropic linear array with an element spacing d equal to lambda by 2, working at a frequency of 12 megahertz when it is functioning in A. broadside mode, B. end-fire mode. There are two parts in this problem. We have to do this problem for broadside mode of operation. Then we have also do this problem for end-fire mode of operation. Find the visible range. This is the problem. Solution. Wavelength corresponding to the given frequency 12 megahertz is 25 meters. Lambda can be obtained using the formula lambda is C by F. C is 3 into 10 power 8 meters per second and F is 12 megahertz. So lambda in this case is 25 meters. It gives beta d. Beta is 2 pi by lambda. D is given as lambda by 2. So it turns out to be pi. Now A part. Broadside operation. When the array is in broadside mode, visible range is beta d2 minus beta d plus beta d2 minus beta d. Therefore, answer to A part of the problem is pi 2 minus pi. B part. For end-fire operation, visible range is 0 to minus 2 beta d. Therefore, in the present case, it turns out to be 0 to minus 2 pi. This is answer to B part of the problem. Another problem, example 3. Find the following parameters in phi domain for a 10 element uniform linear array with an element spacing of lambda by 2 when it is working at a frequency of 60 megahertz. What are the parameters that are required? A. Directions of nulls. B. Directions of grating lobes. C. Direction of principal maximum. D. Directions of secondary maximum. E. Width of main lobe. F. Width of secondary lobes. These are quantities of interest in the pattern of an array. So it's a typical problem, standard problem. We proceed to solve it. Solution. Given that element spacing D is equal to lambda by 2, it is given. Number of elements is given as 10. Wavelength corresponding to given frequency 60 megahertz is 10 meters. So wavelength is 10 meters. Now, a part of the problem. Here we are going to determine directions of nulls. The broadside mode of operation is in force. The directions of nulls, they are given by this formula. Phi is equal to cos inverse plus or minus m lambda over nd. In this relation, lambda by nd is 5. Lambda is known to us, n is given, d is available. So, lambda by nd, it can be found. In this case, it is 5. As it is 5, note that m cannot assume more than 5 because cos cannot have a value which is more than 1. Thus, phi is equal to cos inverse plus or minus 1 by 5, cos inverse plus or minus 2 by 5, cos inverse plus or minus 3 by 5, cos inverse plus or minus 4 by 5, and cos inverse plus or minus 5 by 5. So these are directions of nulls. For end fire operation, directions of nulls are given by this formula. Phi is equal to cos inverse 1 minus m lambda by nd. Expansion gives us cos inverse 4 by 5, cos inverse 3 by 5, cos inverse 2 by 5, cos inverse 1 by 5, cos inverse 0, cos inverse minus 1 by 5, cos inverse minus 2 by 5, cos inverse minus 3 by 5, cos inverse minus 4 by 5, cos inverse minus 5 by 5. These are directions. In both the cases, number of nulls is the same and equal to 10 number of elements. We move to another part, B part of the problem. For broadside operation, the grating lobes occur only when spacing is more than or equal to 1 wavelength. D must be more than or equal to lambda. And their directions are given by this formula. Phi equal to cos inverse plus or minus m lambda by d, where m equal to 1, 2, 3, etc. In the present case, spacing is lambda by 2. This condition is not satisfying the condition for occurrence of grating lobes. Therefore, grating lobes are absent in the present case. Hence, pattern of the array under investigation cannot have any grating lobes. This is for broadside operation. Now we move to end fire operation. They occur when the spacing of the elements is more than or equal to 1/2 wavelength. That is, when d is more than or equal to lambda by 2 in the directions given by this formula. Phi is equal to cos inverse 1 minus m lambda over d, where m equal to 1, 2, 3, etc. In the present case, only one value for m is possible, that is 1. It gives grating lobe direction as phi equal to 180 degrees. End fire means this is the length of the array. End fire means maximum radiation is along the length of the array. Okay. When d equal to lambda by 2, a grating lobe appears. It is along phi equal to 180 degrees, means here. This is phi equal to 0, whereas this is phi equal to 180 degrees. This is the legal maximum radiation. This is illegal and unwanted maximum radiation direction. Grating lobe. Continuation of example 3. C part of the problem. The direction of principal maxima from the definition for broadside is given by phi equal to 90 degrees, and for end fire operation it is 0 degrees, phi equal to 0 degrees. By definition, broadside mode is one which radiates in a direction normal to length of the direction, phi equal to 90 degrees. By definition, end fire mode is one which gives radiation maximum along the length of the ray, that is phi equal to 0 degrees. We move to another part, D part of the problem. The directions of secondary maxima are given by this formula, phi equal to cos inverse plus or minus 2k plus 1 lambda over 2nd for broadside operation. So substituting the values lambda, n, d and giving different values for k, we get phi equal to 72.54 degrees, 60 degrees, 45.57 degrees, etc. on right hand side, and 107.45 degrees, 120 degrees, 134.4 degrees, etc. on left hand side. This is for broadside operation. For end fire operation, directions of secondary maxima are given by cos inverse 1 minus 2k plus 1 lambda by 2nd. By giving the legal values to n, d, lambda and k, we get phi as 45.57 degrees, 60 degrees, 72.54 degrees, etc. To give a better understanding, let me give the sketch of pattern for broadside operation. This is main lobe surrounded by secondary lobes like this. These are secondary lobes. So 72.54, this is 72.54, this angle. 60 degrees, this is 60 degrees. Left side also we have secondary lobes. The direction of this lobe is 107.45. The direction of this secondary lobe, secondary lobe is 120 degrees. These angles are values assumed by phi for the directions. When it comes to end fire operation, this is main lobe, this is first secondary lobe. This is direction of first secondary lobe, 45.57. For this angle is 45.57. Here is another secondary lobe. For this also, angle is 45. Phi is equal to 45.57 degrees. So 45.57, it indicates two planar side lobes. Actually, this is one side lobe. It is one space side lobe, 60 degrees. This is another side lobe. It represents 60 degrees. This one also 60 degrees. Now we move to another part of the problem, E. The first null beam width of main lobe is given by this formula, 2 sin inverse lambda by nd. Lambda is available, n is available, d is available. Substitution gives us first null beam width as 23.07 degrees for broadside mode of operation. In case of end fire mode of operation, first null beam width is given by 4 sin inverse under square root lambda by 2nd. It gives us 73.74 degrees as first null beam width for end fire operation. Continuation of example 3. Another part, F part. The width of the first secondary lobe is angular separation between first and secondary nulls, and that of secondary lobe is the separation between second and third nulls, etc. Okay. Now, the null directions for broadside mode are given by this formula. We have used this formula already in the session. In this problem, example 3 itself, just a few moments back. Phi is equal to cos inverse plus or minus m lambda by nd. Thus, width of first secondary lobe becomes cos inverse lambda by nd minus cos inverse 2 lambda by nd. It becomes equal to 12.04 degrees. Width of secondary lobe becomes cos inverse 2 lambda by nd minus cos inverse 3 lambda by nd. It turns out to be 13.5 degrees. The width of third secondary lobe becomes cos inverse 3 lambda by nd minus cos inverse 4 lambda by nd. It is 16.26 degrees. The widths of other lobes can also be found out in a similar manner. This is for broadside mode of operation. Now we consider end fire operation. Null directions are given by cos inverse 1 minus m lambda by nd. So the width of first secondary lobe becomes cos inverse 1 minus 2 lambda by nd minus cos inverse 1 minus lambda by nd. It turns out to be 16.26 degrees. The width of second secondary lobe becomes cos inverse 1 minus 3 lambda by nd minus cos inverse 1 minus 2 lambda by nd. It becomes 13.5 degrees. Width of third secondary lobe becomes cos inverse 1 minus 4 lambda by nd minus cos inverse 1 minus 3 lambda by nd. It becomes equal to 12.04 degrees. The widths of other lobes can also be determined in the same manner. Now we move to another problem, example 4. How many grating lobes are present in the visible region of the array factor of uniform array having an inter-element spacing of 3 lambda and a uniform phase progression or gradient of minus pi by 3, alpha equal to minus pi by 3. We are asked to determine grating lobes in the visible region. Solution. Given that spacing d is equal to 3 lambda and phase gradient alpha is equal to minus pi by 3. By definition, visible region of array phase angle psi is its range as observation angle. Phi is varied from 0 to pi. Notice range of phi is 0 to pi, not 2 pi. It is simply pi, 0 to pi. Visible region of array phase angle psi is its range as phi is varied from 0 to pi. It is as psi is beta d cos phi plus alpha for the given values in the problem. 6 pi minus pi by 3 to minus 6 pi minus pi by 3 or 5 2 by 3 pi to minus 6 1 by 3 pi. So it is just a range. When phi is 0, what is psi? When phi is pi, what is psi? For the given values of beta, d and alpha. Those limits, those limiting values of psi give us visible region. Now the condition on psi for grating lobes is psi by 2 is equal to plus or minus m pi or psi is equal to plus or minus 2m pi. For each value of m satisfying the above relation gives one grating lobe. The values m equal to 1, 2, minus 1, minus 2, minus 3 give psi is equal to 2 pi, 4 pi, minus 2 pi, minus 4 pi, minus 6 pi, which are within visible range. For values of m other than mentioned here, the psi value falls outside the visible region. Therefore, number of grating lobes that appear in the visible region is 5. Answer is 5. Another problem, example 5. Find the radiation pattern of a 4 isotropic element array with radiators fed in phase spaced lambda by 2 apart by using the principle of pattern multiplication. This problem is based on pattern multiplication. Solution. The field pattern of a uniform linear array is given by this formula. Mod ET is mod E naught mod n sin n psi by 2 by mod sin psi by 2. This is unit pattern. This is array factor. Now, as the elements are isotropic, unit pattern of this array is 1. Unit pattern becomes 1. For 4 element array, the array factor becomes sin 2 psi mod by mod sin psi by 2. What we did here is we replaced n by 4. We got this one, array factor, and E naught is replaced by 1. This is array factor. For the given values, array phase function psi is pi cos phi. How this thing has come into being? Radiators are fed in phase, therefore alpha equal to 0. Psi is beta d cos phi plus alpha. Alpha is 0, therefore psi is beta d cos phi. but beta d in the present case is pi. Beta is 2 pi by lambda. D is lambda by 2. So beta d is pi. Thus radiation pattern, which is product of unit pattern with the array phase function, becomes in the present case mod sine 2 pi cos phi by mod sine pi by 2 cos phi. Another problem, example 6. Find the radiation pattern, phase pattern of a 10 element isotropic linear array with an element spacing d equal to lambda by 2, working at a frequency of 12 MHz when it is functioning in a broadside mode, B and fire mode. Two parts are there in this problem. We are asked to do both the parts, considering broadside operation once and then next end fire operation. Solution. Wavelength corresponding to frequency 12 MHz is 25 meters. So it gives beta d. Beta is 2 pi by lambda. Lambda is 25 meters. D is given as lambda by 2. Okay. So beta 2 pi by lambda. D is lambda by 2. Lambda gets cancelled. We don't require lambda value here to get beta d. Anyway, in the present case, beta d turns out to be pi. First part, broadside operation. When the array is in broadside mode, phase gradient alpha is 0 and array phase function becomes beta d cos phi. Actually, it is beta d cos phi plus alpha. Alpha is 0, therefore it is beta d cos phi. Beta d is pi, therefore psi is pi cos phi. The amplitude pattern then is mod et is E naught mod sin and psi by 2 by sin psi by 2. This one. So it becomes equal to E naught mod sin 10 pi cos phi by 2. What is this 10? N is 10. Number of elements is 10. Substitution gives this quantity divided by sin pi cos phi by 2. So a little bit of simplification gives mod et equal to E naught sin pi cos phi by sin pi cos phi by 2. This one. E naught here is unit pattern as array is made with isotropic elements. E naught becomes a constant. Normalized, when normalized, it becomes 1. Phase pattern, it is given by this formula n minus 1 psi by 2. Psi is known to us. Substitution gives us phase pattern as 9 pi cos phi by 2. Continuation, example 6. B part, end fire mode. When array is in end fire mode, phase gradient alpha is equal to minus beta d and array phase function is beta d cos phi minus 1. This is universal or general expression. For end fire mode, this is the expression. Substituting beta d equal to pi, it gives psi as pi multiplied by cos phi minus 1. Amplitude pattern then is E naught multiplied by sin n psi by 2 by sin psi by 2 mod. But psi is pi multiplied by cos phi minus 1. It gives amplitude pattern as E naught multiplied by mod sin pi cos phi minus 1 by sin pi cos phi minus 1 by 2. As already mentioned, this is unit pattern. It is constant like 2, 2.3, 10, 100, 5. When normalized, it becomes 1 because it is constant because it is array made with isotropic elements. Phase pattern is given by this formula n minus 1 psi by 2. This relation holds good for both modes of operation, broadside and fire. This is the relation, but psi varies. Psi is different for end fire from psi in broadside. Substitution gives phase pattern as 9 pi cos phi minus 1 over 2. Note that phase patterns obtained are valid only when phase reference is first element of the array. In both the modes of operation, if phase reference is the center of array, phase pattern becomes 0. Now we consider another problem, example 7. A linear uniform array of 10 isotropic elements is placed along z-axis. Assuming an element spacing of lambda by 4, find progressive shift half power beamwidth, first null beamwidth, FSLBW. BW stands for beamwidth, FSL stands for first side lobe, directivity for A. Broadside operation, B. Ordinary end fire operation, C. End fire with ID operation. For all these three cases, we are asked to determine alpha, progressive phase shift, half power beam width, first null beam width, first side lobe beam width, directivity. Solution. First we consider broadside operation A. Broadside operation comes into being when alpha is 0. So we need not do any calculations to find alpha value. Broadside operation implies alpha is 0. Half power beam width. It is given by 2 times pi by 2 minus cos inverse 1.39 lambda over pi and d. It is equal to 2 pi by 2 minus cos inverse 1.39 lambda. Let it be there by pi n. N is 10. D. D is lambda by 4. So lambda in the denominator cancels lambda in the numerator. Now in this expression nothing is unknown. A little bit of simplification gives us half power beam width as 0.354 radians. First null beam width. It is given by 2 sine inverse lambda by nd. N is 10. It is given. D is lambda by 4. Substitution gives us a value of 0.82 radians for first null beam width. First side lobe beam width is twice pi by 2 minus cos inverse 3 lambda over 2 nd. Substitution of the given values results FSL BW as 1.28. Directivity for broadside operation is given by 2n d over lambda. It turns out to be 5 in dB. It becomes 7 dB. Before going further, a small explanation for half power beam width, first null beam width, first side lobe beam width. Broadside operation means pattern main lobe exists like this. This is length of the array. This is main lobe. It is surrounded by several side lobes. For the sake of simplicity, I have shown only 2 side lobes. Now, half power beam width means consider 2 points over the main beam where field intensity is 0.707 times maximum value. There exist 2 points. Left side 1 point, this one, right side another point. The angular distance between these 2 points is half power beam width. Then what is first null beam width? Main beam is surrounded by 2 nulls. This is one null, this is another null. The angular distance between these 2 nulls is first null beam width. Usually first null beam width is roughly twice half power beam width. Now what is the first side lobe beam width? See, here you can notice existence of 2 side lobes. Immediate side lobes are called first side lobes. This is one side lobe. This is another side lobe. One can draw a line passing through side lobe maximum like this. Another line side passing through maximum of another side lobe. The angular distance between these two gives first side lobe beam width. Continuation, example 7, B part, ordinary end fire operation. Progressive phase shift is minus beta d. This is standard expression. Beta is 2 pi by lambda. D is given as lambda by 4. Therefore, it becomes pi by 2. If it is minus pi by 2 minus beta d, maximum radiation is along the length of the array like this. This is length of the array. If we choose plus pi by 2, then maximum radiation is opposite to the length of the array like this. Both are called end fire operations, but when it comes to differentiating them, the mode that gives maximum radiation along the length of the array, it is called end fire proper. The mode which gives maximum radiation opposite to length of the array, it is called backfire. So here both are considered. Alpha is plus or minus pi by 2. Plus means backfire, minus means end fire. Half power beam width is given by 4 sine inverse 1.39 lambda over 2 pi nd. Substitution gives us a value 1.21 radians. First null beam width is given by the formula 4 sine inverse under square root lambda over 2nd. Substitution and simplification gives us beam width as 1.85 radians. First side lobe beam width, it is given by 2 times cos inverse 1 minus 3 lambda by 2nd. N is available, D is available. Substitution gives us FSL BW for this case as 2.32 radians. Directivity is given by this formula 4 ND by lambda. Substitution gives us D as 10 absolute value. In terms of dB, it becomes 10 dB. Applying 10 log to 10 gives us 10. Therefore, 10 is equal to 10 dB. Third part of the problem C. End fire with ID operation. Progressive phase shift in this case is plus or minus beta D plus pi by 10. This is progressive phase shift. Beta D is pi by 2. Therefore, plus or minus pi by 2 plus pi by 10. This equality is superfluous. Now, when we choose minus sign here, maximum radiation is along the length of the array. When we choose plus sign, maximum radiation is main lobe is in a direction opposite to length of the array in this direction. But notice whether we go for plus sign or minus sign, beam widths do not change. In B also, whether you go for plus sign or minus sign, here for alpha, half power beam width remains the same. First side lobe beam width remains the same. First null beam width remains the same. Directivity remains the same. So backfire operation and fire operation both give same performance except for directions of maximum radiation being opposite to each other. So in case of C, end fire with ID operation, half power beam width is given by 2 sine inverse square root of 2 into 0.1398 lambda by ND. Substitution gives us it as 0.697 radians. First null beam width, it is 4 sine inverse square root lambda by 4 ND. In radians, it is 1.287. First side lobe beam width in this case is 2 cos inverse 1 minus lambda by ND. It becomes equal to 1.85. Directivity is 1.789 multiplied by 4 times ND by lambda. N is known, 10D is given, lambda gets cancelled because D is given in terms of lambda. So ultimately, after simplification, we get directivity as 17.89. With this, we come to an end of the session. In this session, we focused on linear arrays, uniform linear arrays, and important parameters like directions of main lobe, side lobes, nulls, half power beam widths, first null beam widths, and some other parameters also while they are working in broadside mode, end fire mode, and also end fire with ID mode. Hope this session is useful to you. We meet again soon with a new topic in another session.